Hello everyone! Today's video will be a bit different because we are not going to use the bot to do silly things, but instead I'm going to describe how I run automatic tests for Botcraft, which is the open source library I'm using to create the bots. This video will be a bit more technical than the other ones, so feel free to let me know in the comments if you'd like to see more like this one on the channel, or on the contrary if you'd prefer more bot action. Okay, so when you start developing a software, it's usually very easy to just run it and see whether or not it does what you want. But as soon as it starts to grow, with more and more features and different code paths that can be taken, it becomes harder to think of all the effects one change in the code can have. At the time of recording, Botcraft supports 48 different versions of the game with a lot of different features like world interaction, inventory management, or entity tracking, to name a few. So whenever I change something in the code, I need to make sure I don't break anything else. And to do that, I have 3 different test layers, each of them checking specific parts of the code. They are all fully automatic and run whenever I commit some changes to the code. Let's start with the first layer, the unit test. Unit tests are pretty simple. You take one function in the codebase, you feed it some input, and you check the output is actually what you think it would be. We can check an example with the function compute mining time. It takes as input a block, a tool with optionally some enchantment, and some optional effects like haste, for example. We can run this function against a list of known inputs and check that the return time is actually the correct one. Most of the time, this test will just run silently as the code of this function doesn't change often. But if one day this function is modified, for example to add support for the recent copper tools, then we'll know immediately if the new code breaks something without having to release a bug version and wait for some users to report something is not working properly. Unit tests are great to make sure you build your software on strong foundations. But in our case, with Minecraft bots, the behavior of a bot is not entirely determined by our code. It also depends on the Minecraft server as our bots will interact with it. Which means we can't test everything with our unit tests. And this is why I have the second layer of tests for Botcraft, which I call the online tests. The online tests are much more complicated, and the associated test system is almost a full software by itself. The first thing it does when we run the test is to retrieve the server.jar file for the corresponding Minecraft version and launch a vanilla server on the local network. It also starts to monitor the server process to be able to read the logs and send Minecraft commands directly from the console. The server is not a very complex one. The goal is to have a very stable environment that we can reproduce every time. When the server is started and ready, the test framework sets a few game rules and then it starts to run the test one by one. Each test is composed of 2 parts. The first one is a Minecraft structure block. It will be instantiated on the server before the test runs. It represents the environment required to execute the test. It can be just a few blocks to mine, a full pathfinding course, or some entities to interact with, for example. The other part of the test is the actual C++ code for the bot using the Botcraft library. It can vary quite a bit depending on what we want to test. For example, a very simple test can be just saying hello in the chat and then checking in the server console that the message is properly registered. A more complex case can be a bot that needs to trade some items with a villager and put them in its inventory at a specific position. All the tests registered for the current Minecraft version are executed sequentially. The tests are positioned along the x-axis on the server, and when there are multiple variants for a single test, they are stacked along the z-axis. At the end of each test, the test framework adds a beacon with a color based on the result of the test: green for success, orange for expected failure, and red for failure. There is also a sign added with a TP command to quickly navigate between different tests, and a book in the lectern when the test failed to indicate what went wrong. The exact same information is also logged in the test console, but it allows for quicker inspection while observing the test in real time on the server. The online tests are great because they allow me to test a lot of different configurations in a real Minecraft environment without having to do anything manually. There is one major thing that they can't test on their own though, and that's why we have the third layer, the physics test. Physics is the way your player will move based on keyboard and mouse inputs and the blocks surrounding you. In Minecraft, the physics is entirely calculated by the client with almost no check on the server side. It means that if you're using a custom client or a bot like in our case, and your physics implementation is wrong, then some very weird movement can happen and the server will never tell you something is wrong. So in order to have vanilla-like bots, we need to make sure our physics implementation is doing exactly the same calculations than the original Java client. And this is the goal of the physics test. To do so, it is built on top of the online test system. We also have some structure block to load the test environment, but instead of having code to control the bot, we have this time this kind of file. This is a list of inputs for the bot. Each row is one tick and each column represents one keyboard key. Now our bot will just load into the test environment and follow the file script for the inputs line by line. Each tick, the inputs will be exactly the ones in the file, and at the end of the tick, the position and speed of the bot after applying the physics is recorded in another file. This is great because it's fully automatic, easy to control, fully deterministic and repeatable. Exactly what we want. But we still have one issue. How do we know that this trajectory is the correct one? How do we compare it to the real physics? We can't compare it to a fixed, known trajectory as code for the physics may change from a Minecraft version to another. So we need a way to generate the same trajectory, the same sequence of inputs on a vanilla client for any of the supported Minecraft versions. It's not really possible to do it manually because humans are not reliable enough to repeat the exact same inputs at 20 ticks per second. We could use a custom mod to read the trajectory file and record the position and speed, but we need this mod to be compatible with all versions of the game, from 1.12.2 to the most recent one, or even future ones as we may want to test physics for pre-release versions too. There is no straightforward way to create a mod that would, out of the box, support all existing and future versions. Fabric doesn't support older versions of the game. Forge could work, but we would have to manually keep the Forge version up to date to be compatible with newer releases of the game, and that would be manual work. So instead of relying on a traditional mod loader, we'll use another approach, bytecode manipulation. When you compile some Java code, it's not directly compiled into binary that can be sent to your computer. Instead, it is compiled into what we call an intermediate representation, Java bytecode. This bytecode is composed of low-level instructions like load a value from memory, add two values together, store the result in memory, etc., etc. When you need to execute the bytecode contained in a jar file to actually run the program, you have the Java virtual machine that will read this bytecode and translate the instructions into binaries that can be executed on your computer. This is how you can have the same jar file from Linux and Windows. The intermediate representation is the same, but the translation is done differently depending on where you execute the program. But what's the connection with our modding problem? When we take the official client.jar file from the vanilla game, we can open its bytecode and explore it. More specifically, we can look for the bytecode corresponding to the start of the player.tick function. This is the function that is executed every tick for the current player and does all the physics calculations. Once we have located it, we can inject some custom bytecode instructions. As long as we use the same low-level instructions that can be read by the Java virtual machine and we keep the syntax correct, this is totally valid. Java will just parse these new instructions and translate them into binary for us. So what we do is that we add some instructions to open our inputs file, override the values for key and mouse inputs, and then return to the original bytecode of the function. Similarly, we need to locate the end of the tick function and add instruction to open the trajectory file and write a new line with the current position and speed of the player at the end of the tick. If you have already done a bit of modding, this is the same principle as mixins, except we do everything manually instead of relying on the mixins convenient API. Now, when we run this client.jar file with the additional bytecode instructions, the client will read our inputs file and follow the exact same trajectory as our bot did, and everything is automatized. For any version of the game, we can generate this new modified jar file, making sure the inputs will always be the same. The outputs may change depending on how the physics code in the game change, but we'll always be able to generate the exact ground truth our bot should produce when following the same inputs. Now that we have both the bot and the vanilla client full trajectories, we can compare them. If you go on the Botcraft repository on GitHub, there is a dedicated wiki page with all the physics test results. You can open any version you are interested in and see for each test case if the trajectory is the same or if there is a discrepancy. And in case they don't match, you can click to get the details of the trajectory and see exactly where they started to diverge. This is extremely useful to help identify issues in the physics implementation and also to know if your bot will be fully compatible with a given version or if you should avoid some actions that would result in bad physics outputs. And that's it. This is how I test my Minecraft bot library. If you enjoyed the video, don't forget to leave a like and subscribe, and I'll see you next time. Goodbye.